Hello and welcome. So I welcome you all in today's video. So which will be basically we'll be discussing two dimensionality reduction techniques, one principal component analysis and tSNE. So we'll be looking at details how each differ from one another. So moving on. So what is principal component analysis? So principal component analysis is a dimensionality reduction technique which is used to emphasize variation and bring out strong patterns in a data set. It is used to reduce the size of the data set without compromising on the information which the data conveys. If we have 100 columns, so we try to bring it down to 20 or 30, let's say, and we try to capture the variance in the data set with those 20 or 30 columns, depending on our requirement or need. So how does this PCA work? So PCA has following this set of steps which needs to be performed. So first we start with standardization. PCA is the data have a mean of 0 and standard deviation of 1. Then covariance metric computation amongst different variables which are present. Then we go for eigenvalue and eigenvector calculations, and then feature vector formation, and then recasting back in the data. The original data set is recast into new feature space and which is reduced in size, thus reducing the overall size of the data set. And also in some cases, like if we have six feature, if we can reduce it to two, it can be easily used for visualization even as well. But that cannot be the case if the number of feature even after reducing is more than three, then we cannot visualize those. So next is pre-distributed stochastic neighbor embedding, tSNE. So it is a non-linear dimensionality reduction technique primarily used for data visualization. It maps high dimensional data to lower dimensional space. Basically, PC also does the same, but it uses linear technique. Only a non-linear technique is used. And in a way, it preserves the local structure of the data, which is present in high dimensional. So how does a tSNE work? So first we calculate pairwise similarities, like pairwise between data points in the high dimensional space using a probability distribution that measures the likelihood of one point being about others. So we saw different probability distributions. So here probability distribution comes into picture. Next, we do low dimensional mapping. It then defines a similar probability distribution in the lower dimensional space. Then Kullback and Ligler divergence. tSNE minimizes this divergence between the two distributions, ensuring that points that are close in the high dimensional space also remains close in the lower dimensional space. So I have displayed a table alongside which you can easily see the clear difference between PCA and tSNE. So like feature type of method used in PCA is linear and tSNE is non-linear. Purpose dimensionality reduction emphasize variance, simplify data, and dimensionality reduction and data visualization. Preservation of structure preserves global structure, maximizes variance along principal components. Like we said, we need to capture the variance which is present in the original data. So preserve local structure, cluster similar points together. Neighboring points are displayed in lower dimension in the similar format as it is are present in higher dimensional space. Computation basis like eigenvectors and eigenvalue calculations. Pairwise similarity probabilities, pullback, Leibler divergence. Then output dimension, any number of dimension, typically fewer than original. Like if we have 100, if we have suppose 10, then it can be anything from 1 to 10. Typically 2 or 3 dimensions for visualization because we can visualize only in 3-dimensional at max. Interpretability, it is highly interpretable and it is it is not that interpretable because if we have 10 and if we have 10 features and we want to uh, convert our data into 3 number of features, so many information will be lost and it is not easy to interpret that data. Scalability, efficient for larger data, computationally intensive, slower for large data sets. Then handling of linearity is poor, and whereas in tSNE it is excellent. Application data compression, noise reduction, exploratory data analysis, visualization of high dimensional data, clustering analysis. So complexity. So n cube for eigen decomposition and n square for distance calculation and optimization. Distance metric used in PCA is simple Euclidean distance in transform space and conditional probability based on Gaussian distribution. So I told you in our previous video that probability distribution plays a major role in any machine learning or any uh, any machine learning algorithm, which is visible here, and it is PCA is deterministic and tSNE is non-deterministic, and parameter tuning number of principal components to retain how many principal components we want. And and in tSNE, it is perplexity, parameter, learning rate, number of iteration. These are few of the parameter which can be tuned. So that's all for today's video. I hope you learned something. So have a nice day. Thank you.